everybody, it is all me. Hi everybody, it is me, your all-time favorite guy you never dated in high school. Richard Blyle here with the fourth of 4 videos on the laws of thermodynamics. You know, before we go on, a lot of people have not been asking about quasar. Can you get a shot of this? By t-shirts. And whether or not Quasar is a sponsor of these videos. And I'm proud to say that no, Quasar would not touch me with a 10-foot pole. But listen, just in case you're curious, Quasar is a really cool drive-in theater just outside of Omaha, Nebraska, about 20-minute drive. Definitely worth the drive, and it's where I work. So come on out, see me at Quasar. I work there because you're getting this for free. Okay. 4th video, 3rd law of thermodynamics, which we started with the 0th law. Heat flows from a region of high temperature to a region of low temperature. So it's really the 4th. This is really the last of the 4 laws. It's just labeled the 3rd. First law is, again, I'm going to say this again, I kind of made a mistake at the beginning of the video, and I referred to the first law of thermodynamics as if it was the law of conservation of matter. It is not. First law is conservation of energy. And we showed how energy and work can be interconverted, and we decided that energy cannot be created or destroyed, but it can change forms. Second law of thermodynamics. So the first law of thermodynamics, if energy cannot be created or destroyed, that means the best you can hope for in any process. And like I said, this is not just chemistry. Any process, chemistry, physics, everyday life, engineering, I don't care what you're talking about. The first law of thermodynamics says the best you can do is break even. Second law of thermodynamics dealt with entropy. We decided the entropy of a system can decrease by doing work on the system, but the entropy of the universe can never decrease, which means that if we decrease the entropy of the system, the entropy of the surroundings must increase at least as much as the entropy of the system decreases, and probably more. If it does not increase, that's usually an ideal situation, and like ideal men, those situations just don't exist. Entropy and enthalpy. Enthalpy is what we call the chemical energy, so you'll hear me talk about enthalpy a lot. Those are the 2 driving forces, okay? Those are the things that determine if something is going to occur or not. And something can be as abstract as love. Are you in love? That has to happen according to the laws of thermodynamics. It may seem a little bit strange that something as esoteric, as ethereal as love has to follow the laws of thermodynamics. But if you get, I apologize to my poet friends out there. If you think about what love really is, it's feeling, and feelings occur in the brain. And when you're in love, the brain releases happy chemicals, like serotonin. Those are chemicals. And the process of releasing those chemicals, the process of the electrons being transferred between nerve cells, the connections being made between cells, those are all processes. Those all must follow the laws of thermodynamics, which means, yes, if you're in love because the laws of thermodynamics allows it to be so. It's wild. But we know that energy tends to go from high to low energy. Entropy tends to go from low entropy to high entropy. But there are processes on both sides where the opposite occurs. When water evaporates, It absorbs heat. That's why we sweat. The process of evaporation absorbs heat. That should not be happening because you're going from low energy to higher energy. That's why the heat is absorbed. And that is not what energy wants to do. As we work on roads and repair the damages from the winters, as we're seeing now, the entropy of the roads is going from high to low. That should not be happening, but we know that it does. The two driving forces, entropy and enthalpy, energy and entropy, are the two driving forces for any process. And they're in constant flow. If energy is going up, I can guarantee you entropy is going up as well. As we work on those roads to bring the entropy down, we are releasing a lot of energy from fossil fuels with those machines, with the trucks that are doing the work. So the entropy of the roads are going down, and we're burning a lot of energy to do it. So energy is going down as well. That's how the work is done. And yes, the entropy of the surroundings is also increasing. As we are going from a liquid to a gas in evaporation, those molecules are going from a small confined area on our skin out there into the environment. The entropy is going up tremendously. So as the energy goes up, the entropy also goes up. So the two driving forces, one of them has to be driving any natural process. Now there are processes and they're coupled, okay, in your body. It's possible to have both entropy increase and energy increase if there's a driving force behind it, if there's a second reaction, if there's something that is forcing that to happen. So yeah, we can also talk about coupled reactions, which is another story altogether, but something has to be providing that energy in order for that process to occur as well. So, let me zoom in on my chalkboard here. And I brought this analogy before. It's like yin and yang, all right? The two driving forces of any process is entropy and it's enthalpy, which I'm going to write as H. Remember, H is enthalpy, which is a form of energy. It's heat, basically. And a process that occurs, if they're both working together, which sometimes happens as well, like when dynamite explodes or when fireworks explode. Energy is going down because it's a lot of stored energy in fireworks, a lot of high potential energy. You burn it and it goes to carbon dioxide, water, and that energy goes down. So that is very much enthalpy. And then you're going from a tiny little firecracker to basically blasting somebody's finger off. That's high entropy. So you're going to low energy and high entropy. You're doing them both. But the third law of thermodynamics asks this. How do we know which one? How do we know which one of these has the upper hand? Yin and yang, it's not a competition. They're just in flow. But one of them has to be in power, and that's what the third law of thermodynamics tells us. And I'm going to put an equation up here, talk a little bit about the implication of the equations. I'm going to talk about how this is determined, but we're not going to go into any real examples. But it's fascinating. The third law is fascinating, and I'm going to explain why in a minute. And then maybe we'll talk about a few modern examples and some things you might have been hearing. Doesn't make sense. Excuse me while I turn down the Beatles just a wee bit. Okay. So, third law of thermodynamics. Let's talk about the two things we've already discussed. So change, remember, change in enthalpy. Change in enthalpy, oops, almost did that backwards. If change in enthalpy is negative, it's less than 0, it is exothermic. Heat is given off. And it is favored. But there are processes where change in heat is endothermic. That means heat is absorbed. It is not favored. Okay? There are processes where, remember, delta is change in. That's all that means, change in. So you have a process that starts with a certain amount of energy, ends with a certain amount of energy. Delta is always final minus initial. And in enthalpy, if that's negative, it's favored. But we also have entropy. Entropy can go down. You know what? There should be a thermodynamic term for this. I'm not quite sure what it is. I'm going to look that up after this video. Entropy can go down. It is not favored. Or entropy can go up. And I put this arrow the wrong way. Or entropy can increase, which is favored. So it wants to have exothermic and increased entropy. That's what all processes really want. Enthalpy is energy, is it going up or down? Entropy, we talked about that. You can think of it in terms of chaos if you prefer. Not a good way to think about it, but it's fine. It works for our purposes. So how do you know if a process is going to be favorable or not? Favorable means it will occur naturally. It is spontaneous. The word I'm looking for is spontaneous. Spontaneous processes occur naturally. Spontaneously. That's where the term comes from. Or how do you know if it won't? How do you know if we have to put something else in there to force that reaction to go? Right now, my hybrid vehicle is plugged into the power of my house. It is forcing the batteries to charge, which is not a natural process. Not a lot of entropy change there. There's some, there's internal, which is really what entropy is. It's internal changes. So I'm coupling it with the power that comes from the house, which is connected to the power grid out there somewhere. A lot of people think that, I've been told that, you know, electric vehicles, you don't have to pay for gas, so it's free. No, it's not free. Internal combustion engines localize the energy that the car uses in the car engine. Okay? Electric vehicles decentralize that energy. That's all they do. And that decentralized energy goes to the power grid. And you have to pay for that. Your electrical bills go up. If you don't believe me, go to a charging station sometimes. And they'll charge you for 25 bucks to charge up your vehicle. That's real money. So yeah, you're still paying for it. It's just that you're paying for it. Hello, Star. It's just that you're paying for it in a different different venue. You're paying for it through the network, which, you know, hopefully if everyone goes electric, those will increase. Now, you might also think that with an electric vehicle, you're decreasing your carbon footprint, which you might be, but not necessarily. Here in Nebraska, as a state, we are considered one of the top 5 states for solar energy potential. Okay? We are one of the top 5 best states to put solar panels in. We're also ranked one of the top 5 states for wind energy. We are one of the top 5 best states where we could put in wind turbines. We are also in one of the lowest 5 states for using either. Here in Nebraska, we are still burning coal and oil in our power plants. So my carbon footprint is not really decreasing. If anything, it's increasing. Okay? Because for me to charge up my car, it goes to a power grid that uses fossil fuels. So I'm still burning fossil fuels to drive, even if my car is electric. It's an effort, honestly. But I'm not naive. I understand where this power comes from. And the only way that I could reduce my carbon footprint is if our power grid here in the state switches over to clean energy. Then my carbon footprint will decrease. But until then, all I've done is decentralize where that fossil fuel is burning. I've done the best I can. I vote for clean energy, but it's up to the state really to do it. And I'll tell you what, the first law of thermodynamics tells us I cannot get more energy out of my car than I put into it. So when I drive, the amount of energy that I drive cannot be better than the amount of energy I put into it. So the best I can hope for is to break even, but that's ideal. The second law of thermodynamics tells us that in charging my batteries, there are internal processes that will chew up some of that energy and will no longer be available to drive my car. There's energy lost in any process. That's the second law. There's always energy lost in any process. That's the second law. Best you can hope for is to break even. Yeah, good luck on breaking even. That's what the two laws together say. So, I'm actually going to get less energy out. And by the way, batteries are the least efficient method, even today, for energy storage. They're getting better. They're getting much better. There's a lot of work that's being put into it. But still, there's a lot of energy lost in batteries. So that's where a lot of that entropy is lost. That's where a lot of that internal energy goes. So we have a process that involves both enthalpy and entropy. How do we know which one is on top? How do we know if that process is going to occur or not? That's the third law of thermodynamics. It is called free energy. In chemistry, it is called Gibbs free energy. No, not named after the 70s band. Gibbs free energy. Free energy is not free energy. It's like going to, if you want to go to a place where they're advertising free beer, and it turns out the name of the band is free beer. You're not getting free beer, but there's free beer. That's what free energy is. It's not free. This is the amount of energy available to do work. Okay? This Gibbs free energy, which is a capital G, this is the actual amount of energy that my car gets when I charge it up that is available for driving. This is the amount of energy that can be applied for driving. That's the free energy. How much energy is really useful energy? And it's a very cool and excessively insightful equation. It looks like this. Your change in free energy is equal to your change in enthalpy. That's your first law of thermodynamics. Minus T delta S. I'll figure, yeah, that's correct. So here's your second law. First and second law goes into your third law of thermodynamics. Enthalpy and entropy. T is temperature. But it's not just temperature. It must be an absolute temperature scale. Now we talked about in the zeroth law how temperature is related to motion. The higher the temperature, the faster molecules and atoms move. Well, that means there has to be a bottom limit to that scale. There has to be a temperature where everything, all motion stops. That is absolute zero. People are used to the Kelvin absolute temperature scale. In degrees Celsius, you add 273.15. Everyone forgets the 0.15. It's not 273 exactly. It's a little bit more, 273.15, and it goes beyond the 5 as well. I mean, they're down to millionth of a degree. That's how close they get, but we can never actually reach absolute zero. It's like traveling at the speed of light. It's a limit. You can't actually reach it. Okay, so you have to use an absolute temperature scale. It doesn't have to be Kelvin. As it turns out, there are other absolute temperature scales. The other really big one is called Rankine, R-A-N-K-I-N-E. The Rankine temperature scale corresponds to degrees Fahrenheit, just as Kelvin corresponds to degrees Celsius. And if I'm remembering correctly, and I may not be, look this up if you need it. If you add, I believe it's around 459. If you subtract, I think 459 from degrees Fahrenheit, you will have an absolute temperature scale. Mathematically, this is important because oftentimes we divide, in many equations in chemistry, we divide by temperature. So using an absolute temperature scale means you can never divide by zero, because the absolute temperature scale never reaches zero. But it's more than that. Conceptually, it's when all motion stops on an atomic level. So how do we know if a process is spontaneous or not? Well, we've talked about how to calculate. You can calculate their tables. They're thermodynamic tables for different chemicals and whatnot that talk about, that give you sort of a relative enthalpy and a relative entropy. So in a process, you can actually look. Here are the products. The enthalpy adds up to this, the entropy adds up to this. And here are the reactants. The enthalpy adds up to this, the entropy adds up to this. Take your enthalpy, you take your product values minus your initial values, and you get delta H, you get delta S. You can calculate those. You can get real numbers out of this. But if delta G is less than zero, if delta G is negative, your process is spontaneous. And I'm just doing this for completeness. I think the implications of this is far more interesting than the details. But if delta G is positive, the process is non-spontaneous. Which reminds me, yes, that is correct. This is how I know it's correct. Okay, fine. So what? This is your question that you should be asking you right now. So what? Well, first of all, I want you to notice that mathematically, if delta H is positive, if this term is positive, it can still be spontaneous provided this term is large enough. So you can have entropy-driven processes like ammonium chloride dissolving in water. And if delta S is positive, you can still have spontaneous processes provided delta H is negative enough. So this equation, this simple little equation, tells you if that process is going to be spontaneous or not. It tells you if it's going to be enthalpy-driven or entropy-driven or both. Fine. That's fine. Let's talk a little bit more about the implications, though. Because this is something that fascinates me. These numbers, okay, they change a little bit with temperature. Your enthalpy will be a little different if you're under high temperature versus low temperature, but not much. Not much. This is something that just blows my mind right here. Temperature only influences the entropy term. That blows my mind. It doesn't influence entropy itself. I mean, again, a little bit of fluctuation. But it actually increases the importance, the significance of the entropy. Not the enthalpy. The enthalpy is fixed. It's constant. It does not matter. But the entropy term, the importance of the entropy, increases with increasing temperature. The importance of the entropy decreases with decreasing temperature. When it gets cold out, and do you ever notice that batteries tend to die in the winter? If they're going to die, they die in cold temperatures. It's because of the entropy term. It's the entropy that makes it die. And if it's dead, that means that somewhere that internal entropy process, that's negative. A negative times a negative is a positive. And when your battery dies, it's because this term overwhelms that term. That's always fascinated me. Temperature doesn't change either of these terms, but it does change the importance of entropy. And this is something that scientists forget. Even in chemistry. I was a visiting scientist, and I'm not going to name drop, but I was fortunate to have worked with a Nobel laureate. Wonderful, wonderful man. No, I met many Nobel laureates in my day, and I'll tell you the truth, they are cool people. Because they've already proven everything. They don't have anything left to prove. So they tend to have their own labs. Anything that comes out of it gets their names on it, and their graduate students and postdocs, they all have their own grants, so they don't even have to look for grants anymore. They can just chill and relax. And that's what they are. They are chilled and relaxed. They are very cool people. Anyway, carbon clusters was a big thing then. The so-called buckyballs. It's just carbon, usually in a little sphere. Carbon 32 was a big one. Carbon 64. There was one that looked like it was a potential cure for AIDS. Because there was one that was a sphere of carbon that was just big enough and had an affinity for the HIV virus. And there was a pocket in an active site in that virus, and those buckyballs fit right in them. Deactivated the virus because they couldn't, their active site was occupied. They couldn't do their function. Nothing seemed to come from it, as far as I know. And I'm guessing it's because viruses evolve. So yeah, it probably worked for a while, and then the viruses evolved enough so that the buckyball didn't quite fit as well, and all of a sudden it just... But one of the more interesting clusters was carbon 13. That was mine. And you can actually look up a paper of mine. Sadly, it did not have the name of, well, it kind of did. In the acknowledgments at the end, I was working with a new guy, and he wanted his new institution name on the paper, which broke my heart. because now nobody knows that I've been affiliated with that other big school. But I did think that Nobel laureate in the acknowledgments in the bottom. But here's the question. Carbon-13, is it a ring structure or is it a linear structure? And there are a lot of publications on carbon-13. Some of them said, no, we did our studies and it's a ring. And other studies said, no. According to this study, it's just a chain. This was the secret. This was my publication because I did quantum mechanical calculations and I calculated enthalpy and entropy for the ring and the chain structure. Well, the chain has a higher entropy. Okay? And I realized that if your temperature was low enough, the entropy was a less significant factor and you would get a ring. But at higher temperatures, the entropy becomes more important and you would get a chain. And I calculated what I call the crossover temperature. At this temperature, you should have, it could go either way. So go below that temperature, you have a chain. You go above that temperature, you have a ring. Simple. I mean, this comes from freshman chemistry. Man, we teach this in freshman chemistry. And I published a paper from a freshman chemistry equation. You have to be careful. I'm talking a lot about electric vehicles. Let's go back to electric vehicles for a minute. Because today, my vehicle is no longer a hybrid vehicle. Mine is now called a plug-in hybrid vehicle because I can plug it in. And I went with that because in my humble opinion, we don't have the infrastructure for electric vehicles yet. With a purely electric vehicle, it still takes a good 30, 45 minutes, an hour, even with a rapid charging station to charge it up. And we don't have enough of those stations from coast to coast. You can only go about 300 miles on those things. And you have to charge them up. And if you don't make it to the charging station, you're stuck. What's worse? If you make it to a charging station, there are all kinds of different plugs out there. I'm getting grandfathered in. My hybrid was built in 2017. I can guarantee you that my plug will not fit modern plug-in stations, charging stations. Tesla seems to have cornered the market on those charging stations, and a lot of places are going to a Tesla-style plug, which is a step in the right direction. I'm getting left out of the equation, but that's okay, because at least we're going to have a uniform system. If I go to a gas station somewhere, I know that that pump is going to fit my gas tank. We need that for electric. But anyway, I went with what's called a plug-in hybrid. So if the battery dies, which it often does on my trips, it just switches over to gas. It's fine. These days, car companies and dealerships are trying to sell you on what they call hybrid vehicles, but you cannot plug them in. These hybrid vehicles recharge the batteries by driving and braking. All right? In other words, for those electric vehicles, they're not electric. Those are gas vehicles. That's all they are, because you can't plug them in. I believe that if we are to survive, we need to do two things. We need to be better at conservation of energy, that means better efficiency, and we need to be better at diversity of energy sources. If we went pure wind, we're going to kill ourselves just as fast as we do with pure fossil fuels. We need diversity. We need wind power, we need solar power. We need to phase out fossil fuels. because we've already done too much damage to our environment with that. Reminds me of something else I want to talk about. But if you're charging your vehicle by driving it, all that power is coming from your fossil fuels. All that electrical power is coming from your fossil fuels, which means, according to the first law of thermodynamics, you cannot get more energy out of your fossil fuels than you're putting into it. At best, those cars are breaking even with the amount of gasoline that you're putting into it. But because of the second law of thermodynamics, they're not even that good. Consider this. When I am driving in my hybrid, when I am driving on pure gasoline, I am getting around 40 miles a gallon from 2017. I was talking to a fellow that drives a high efficiency hybrid car that you cannot plug in. He's getting about 32, 35 miles per gallon. Does that make sense? It does. Because in order to have a hybrid, you're adding weight to that vehicle by adding more batteries and by adding more generators. And while you may be recharging those from driving, going down hills, braking, you're not going to be able to recharge them with 100% efficiency because some of that energy is lost. They would do better. This is why I think it's nonsense. And I understand what they're doing. They're trying to recapture some of that kinetic energy. I get that. Laws of thermodynamics says you're going to fail. They would do better to take those batteries out, take those electrical generators out, and go with a lighter vehicle, which will improve fuel economy. So by actually trying to recapture that energy, laws of thermodynamics tells us they're going to make it worse. Today they are trying carbon dioxide capture technology. Laws of thermodynamics tells us that's going to fail. Carbon dioxide, the problem with this, and people say, oh, plant trees to get rid of carbon dioxide. No. Planting trees will help a little bit in the short term. But not in the long term. The reality is, when I burn gasoline in my car, and I'm painfully aware of this, when I burn gasoline, I'm taking carbon that was separated from the carbon cycle and I'm putting it back into the carbon cycle. All those oils, all that coal was buried in the ground. By digging them up and burning them, we insert them into the carbon cycle. And trees will take them out temporarily, but eventually those trees are going to die, they're going to burn, they're going to rot. Something is going to happen. All that carbon gets pumped right back into the atmosphere. If it's a sequoia, maybe hundreds, thousands of years later, but it's still in the carbon cycle. So the only way to mitigate is to stop bringing carbon out from the ground and burning it. When you try to mitigate, now they're building these plants that try to capture carbon dioxide. They're putting a lot of energy into that. A lot of that energy is lost, and they're trying to form basically limestone. Okay. That's going to trap that carbon dioxide for maybe a few thousand years. But guess what? According to this equation, that limestone is going to break down and all that carbon is going to go right back into the atmosphere. Now we are talking the difference between kinetics and thermodynamics. Thermodynamics, if you have a diamond ring, Thermodynamics tells you that that diamond is being converted from the diamond form of coal into the graphite form of coal. So look at those diamonds on your fingers and tell me if you see any discoloration or any specks, because thermodynamics says that diamond is not going to stay a diamond. If you don't notice those specks, that's because of kinetics, which tells us yes, it is turning into coal, and you might notice a change in a couple 100 million years. Just because something happens doesn't mean it happens quickly. This wraps up. I think I've talked about everything I wanted to talk about. But don't buy it. You know, if someone tells you that, you know, hydrogen is free fuel. That's the other one, is hydrogen power. Well, guess what? That hydrogen has to be generated by electrolysis. And electrolysis uses electricity from our power plants. So we're right back to it. If you generate hydrogen, first of all, if you don't have a green power grid in your state, you're still putting up carbon dioxide, even with hydrogen batteries. And yes, the exhaust of hydrogen batteries is nothing but water. It's where it came from, but that's the thing. It's giving off water, so you take water and you electrolyze it, and you get hydrogen gas. You also get oxygen gas, but we capture the hydrogen. And you go back and you use it in, hopefully, an electrolytic cell, because if you just burn it, highly inefficient. You're going to get much better efficiency with a hydrogen battery. But you're starting with water, which has an energy level here. You're ending with water, which has an energy level here. Guess what? The net energy, delta H, equals 0. You don't get any more energy out of it because you're ending up with the same thing you're starting with. So the total energy is 0 now. Maybe you didn't put the energy into it. Somebody did. And because of the second law of thermodynamics, that process is going to cost you energy. So even with a highly efficient electrolytic cell that uses hydrogen to generate electricity, you're still losing energy because of the second law of thermodynamics. That still costs you something. When I taught, I used to give this little spiel. I used to tell my students that all I have done today is give you a new tool for your toolbox. That's it. In these 4 videos, I have given you a new tool for your toolbox. Now, if you're like me, and my friends are going to laugh when they see this video, because they know that I love tools, but I hardly ever use them. So what happens? They go into the garage and they rust. That's an option for you. You've watched these videos, you can say, okay, well, I feel smarter now, and just never think about it again. And then all that knowledge rusts. It atrophies. But by looking at the laws of thermodynamics and thinking in terms of these 4 laws, and I've given you everything you need to at least understand processes, it's a very powerful thing. You can look at what people are trying to sell you and think to yourself, well, now wait a minute, how much energy can I really get out of that? And what's the cost of that energy? And you can decide if that makes sense or not. Is solar power really free? Well, I mean, a lot of environmentalists will say, well, no, because you have to dig it up and all that kind of stuff. Okay, that's true, I'll give you that. But even if we recycle, what is solar power? It's converting sunlight into electricity. And if we are capturing sunlight and converting it into electricity, that means that that sunlight is being trapped and is not being reflected back out into space. What do greenhouse gases do? They trap the light so that it cannot be reflected back into space, and trapping too much of it means that excess energy is causing global warming. Guess what? Too much solar power, we are trapping sunlight and keeping it on the earth. That is going to increase temperature as well. Wind power, too much wind power will affect, I don't care what anybody says, too much wind power will affect the jet streams around the earth. It's going to slow them down, and it's going to cause problems. It's going to actually affect the weather and probably also cause global warming. Too much reliance on any one form of energy, just like we have been relying too heavily on fossil fuels already, is going to be damaging and is going to cause a problem. We need a diverse solution. We need to look at wind power and solar power and hydropower and geothermal power. We need to look at incorporating all of it as best we can so that we don't have to over-rely on one of them. But even at that, if we are not conserving our energy, we're dead. That's it. We're dead. And with that happy note, I hope you learned a little something here. I hope you enjoyed it right up to the bitter end, which it was a bitter end, wasn't it? And meanwhile, I am out of here.